topic of today's video is the analysis and the report for the alkylbromide synthesis, nucleophilic substitution of an alcohol to synthesize an alkyl bromide. One of the methods that you will be using for the analysis is nuclear magnetic resonance spectroscopy. You've seen this before, but we'll go ahead and give a recap of that. Remember, there are three things that we look at with NMR. One is the chemical shift. This is the frequency. It's actually an adjusted frequency, but a frequency, and it gives information about the environment of the nucleus. This is similar to the wave number or the frequency in IR telling us a type of bond. This gives us information about the hydrogen that we're looking at. We also look at integration. The peak area is directly proportional to the number of nuclei, so we can determine whether this is one hydrogen or two, so it gives us numbers. And then the coupling, often called splitting, peaks are split by neighboring hydrogens or neighboring NMR active nuclei. Specifically, we're looking at hydrogens. And this gives us information about what pieces are put together so we can assemble a specific structure. So let's start with chemical shift. The electrons that are around the nucleus do shield it and change the frequency a bit, and so we can get information about the environment or the type of hydrogen based on the shift. We do normalize the frequency, which is why we call it a chemical shift rather than a frequency, because absolute frequencies are dependent on magnetic fields. And you've seen this table. This is similar to the one for IR. This is a correlation table. And in particular, in this table, there are two rows that are relevant. In fact, the same two rows that were relevant for the alcohol analysis when we did the ester hydrolysis. One of those is this row here. Peaks between about 0.7 to 1.8, give or take a little bit, are saturated alkyl hydrogens. So methyl, methylene, methynes, these all show up in about the same region. The other region is 3 to 4.5 ppm. This is the region where we find hydrogens that are bonded to the same carbon as an electronegative atom. So alkoxy, this was relevant with the alcohols, but also alkyl halides, which is relevant to today's experiment. So the hydrogen on the same carbon as the bromine is going to show up at around 3 to 4.5 ppm, so we can identify that using the chemical shift. Integration, as I've mentioned, is the peaks are directly proportional to the number of nuclei, so we can use this to determine whether we're looking at a CH3, a methyl group, or if the integration is 1, a methine, a CH. If it's something like 6, it's probably going to be 2 methyl groups, since we can't have a CH6. But this gives us the number of hydrogens. And then splitting, the peaks do split. If there are no hydrogens on the neighboring carbons, then the peak is going to be a singlet. If there is one neighboring hydrogen, meaning a hydrogen on one of the adjacent carbons, then the peak from the hydrogen of interest is going to be split into a doublet. If there are 2 neighboring hydrogens, it gets split into a triplet. 3, it gets split into a quartet. So basically the number of peaks in that multiplet is going to be 1 more than the number of adjacent hydrogens. The peaks do have symmetry. Note for the doublet we have 2 peaks of roughly equal intensity. For the triplet we have a 1-2-1 pattern. Notice these 2 outer peaks are roughly half the size of the center peak. So that 1-to-1 ratio. Or for the quartet, these 2 outer peaks are approximately 1/3 the size of the 2 central peaks. And a sextet, the 2 outer peaks are about 1/10 the size of the center ones, or 1/5 the size of these other 2. And this follows Pascal's triangle, but the peaks are fairly symmetric. if you don't have a nice pattern like this, it usually means that you have overlapping peaks, and we simply call it a multiplet rather than giving it a specific name. All right, so let's see how all that is used. Note first that we have this axis along the bottom, our x-axis. The units aren't here. We should have units ppm, stands for part per million. This is our normalized frequency. The numbers in red, these numbers, the ones right underneath the peak, are the integrations or integral values. Remember that integral values or actual integrations of hydrogens have to be whole numbers. We can't have 3/4 of a hydrogen or half a hydrogen. So we need to normalize these numbers, basically set them to whole numbers. The easiest way to do that is simply to divide each of the numbers by the smallest, since the smallest number we can have is 1 hydrogen. So we would divide 0.87 by itself. We get 1, which means this is 1 hydrogen. 1.74 divided again by 0.87, we get 2. So this represents 2 hydrogens, likely a methylene. And this one out here, 5.22, again divided by 0.87, and we would get 6. So this represents 6 hydrogens. As I mentioned before, we can't have a CH6. Carbon can't have more than 4 bonds, so most likely that's going to be 2 methyl groups. If we had a ratio of 1 when we did our math to another peak being 1.5, in that case we would assume that this is really going a 2 to 3 ratio. We would simply double it. On the other hand, if we have something like a 1 to 1.9, we would just simply round this to a 1 to 2 ratio. So if it's close to a whole number, we round it. If it's about a half, we would simply double it to get whole numbers for this. So writing that up in the corner there, we have a CH2, a CH, and likely 2 CH3. So at this point, we know something about our structure already. Whatever this is, it has 9 hydrogens, which would mean this is likely a butyl bromide of some sort. And here we have the actual fragments written above the pieces. And so the next step is to figure out what types of hydrogens they are. Basically, we're looking at the different regions. Again, these out here are all in the alkyl region, so these are alkyl CH. If we go back to our correlation table, in the 3 to 4.5 range, this region out here is where we have CH that is bonded to an electronegative atom. In this case, it would be bromine, meaning that this is a CH2Br, and the others are plain alkyl CH. They're bonded to other carbons. And so we determined that by chemical shift. So the last thing we need to do is determine how we put this together. Really, with the bonds we have, there's only one way to assemble this into a molecule, but we'll go through the steps anyway, looking at the splitting for each peak. And we can start with the bromomethylene group. This is a doublet. There are 2 peaks, roughly equal intensity, so this is a doublet. A doublet indicates that there is 1 neighboring hydrogen. So that means our CH2 is bonded to a carbon that has only 1 hydrogen, which would mean it's the methylene that's around 1.7 ppm, meaning that these 2 pieces are bonded together. So the next step, we will go to the peak around 0.95. That is also a doublet. So again, this means 1 neighbor, meaning those 2 methyl groups are bonded to a carbon that has only 1 hydrogen. So these are bonded here and here, giving us this structure. We don't really have to analyze that last peak, the one at 1.7, but if we did look at it, we do have one peak here. We've got two more, making 3. We've got 2 more, so 5. 2 more. We've got at least 7 peaks. If we blow this up, we would find that there are in fact 2 more very small peaks right at the edge. They don't show up, they're a little small to see in the spectrum, but if we expanded that, we could see there are actually 9 peaks there. And this is one problem with trying to analyze the peaks with high splitting, is that unless you can actually do the expansion, sometimes it's easy to miss the small outer peaks. But 9 peaks is a nonette, meaning there are 8 neighboring hydrogens. And the way you get 8 would be to have 2 methyl groups, 3 each, plus a methylene. So we have 3, 6, 2 more is 8. And so this hydrogen has 8 neighbors, and we would know that by looking at this multiplet here and recognizing this is a nonette, or 9 peaks. And so we have a very consistent structure. Now when you do your analysis, you do need to do what I've just done, go through the integration, the chemical shift to determine which peak has the bromine on it or which carbon, and then finally put the pieces together with the splitting. And it's easiest to do that and explain what's going on if we label our hydrogen so we can refer to a hydrogen as hydrogen A. And so in the discussion you could say the peak at 3.1 ppm correlates to hydrogen A, and your reader would know what you're talking about. So you do need to have a structure of the bromoalkane, and you need to have it labeled. If 2 sets of hydrogens show up on the same peak, give them the same label. So we have one peak here at the 0.95. It represents both methyl groups. And so we give them the same label because they are represented by the same peak. When you get into Organic 2, you will learn about equivalent nuclei, and you will label them accordingly. But for now, if they're from the same peak, give them the same label. All right, so let's take one more example. This is a more complex structure, but we approach it exactly the same way. We want to normalize our integration, so we divide each of these by 1.37. So this would be 1. If we divide this one by 1.37, we get 2, 3, 2, and 3. And so we have our ratio of hydrogens. Again, if any of these were a half, we'd just simply double everything, but these give us whole numbers, or very close to it, minimal rounding. And so we know we have a total of 11 hydrogens. This would be consistent with some kind of bromopentane. So again, we go on then to, after labeling the peaks with the types of hydrogens, a methine, a methylene, a methyl, a methylene, and a methyl, in that order. We then look at the chemical shift. Again, in this 4.5 to 3 range is where we find our alkyl halide. So the hydrogen that is on that sextet out about 3.7 ppm is the one that has the carbon with the bromine on it. And the rest of them are all again in about the 1.7 or 1.8 to 0.7 region. These are all the plain alkyl hydrogens. So the next step is, how do we put this together? And again, for that, we look at splitting. In fact, in this case, there's more than one way to assemble this into a structure, so we do have to use our splitting. And so if we look at that first peak, this is a sextet. We've got 2, 3, 4, 5, 6 peaks. So sextet means 5 neighbors. We can't have a CH5, but we can get that by having a methyl and a methylene. So this is bonded to a CH2 and a CH3. Now we have 2 of each. So we can continue looking at the splitting. We'll start with the first, or at least the methyl that's closest. This one here. at about 1.45 ppm. That is a doublet. A doublet means that we have one neighboring hydrogen, and only one of these other peaks represents a CH1, and that is the one with the bromine on it, which tells us that this methyl group is the one bonded to that CH. So it's also bonded to a CH2, but we'll get to that. But while we're looking at the methyls, we can go ahead and look at the other methyl as well. This one at about 0.9 ppm, this one is a triplet. Triplet tells us that it is bonded to one of the CH2s. And again, we'll continue the analysis to find out which one. Okay. But so far we have this structure. So we'll look at this peak, the methylene, about 1.3 ppm. That one is again a sextet. It's not quite symmetrical, but very close. These two peaks are very similar height. These two, again, are very similar, and then the outer ones are equivalent. But again, 6 peaks. So this is a sextet, telling us that this CH2 has 5 neighbors, meaning it is bonded to a CH3 and a CH2. Going back to this triplet, it is bonded to a CH2. Well, this CH2 is bonded to a CH3 on one side and a CH2 on the other. The only other CH2 is this one. So we've got a structure then that looks like that, where we have a CH2, CH2, CH3. And of course at this point we can put our last piece together. We're going to have this bonding here, but we'll continue to analyze our splitting. Just go through the motions. This last peak at 1.7 ppm, this is a quartet. We have 2 peaks here, and then 2 more here. Again, it's not quite symmetrical, but very close, but still 4 definite peaks, so it is a quartet. There are 2 ways to have a quartet. Either it's going to be 3 neighbors, which will be either a methyl, a CH3, or a CH2 and a CH. And at this point, we have what's left is a CH on one side, a CH2 on the other, so these are bonded together, giving us this structure here. And so this is 2-bromopentane as our final structure. Again, we do need to label our hydrogens, so do draw a structure of the bromo alkane that you have and label the hydrogens. In this case, each set of hydrogens has a single peak, so none of them have the same label on them. Okay. This is the process you need to do for your analysis as well. And we'll get back to this just a little bit when we talk about the report. So same guidelines as before: name, date, section number, unknown code. Don't forget to put which unknown you're assigned. Academic integrity statement. Abstract. The abstract is a short statement of what you are attempting to do, very briefly how you're doing it, and a summary of your results, and of course how you achieved or determined those results. An example is written below. 1,4-methoxyphenyl-2-methylpropane-1-ol was synthesized in 47% yield. So we're telling what we did. We synthesized that alcohol, and we are giving the yield. We do give the name of the specific compound, so don't simply say an alkyl bromide was synthesized. Name the alkyl bromide that you have. The type of reaction is also given. In this case, it's a Grignard reaction. Of course, in your case, it's a nucleophilic substitution reaction, as well as the reactants. Again, the specific reactants are named. For example, here the reaction of 2-bromopropane with magnesium metal. And so in your case you would name the specific alcohol and the fact that you're using sulfuric acid and sodium bromide for the nucleophile. Again, specifically, name your reactants, name the product, and name the reaction type that you are using. And then, of course, we're always giving results. So you would also state the yield that you obtained it in and how you did that analysis. In this case, infrared spectroscopy and proton NMR spectroscopy. In your case, you would also be using boiling point and gas chromatography. But we do not recap the procedure. We don't mention the reflux or the distillation or the fact that we washed it. None of that is in the abstract. That will, of course, be in your procedure. Chemical equation. Again, show the equation that you're doing for the specific compound. Don't show a generic one for N-alkyl halide, N-alcohol going to an alkyl halide. Show the specific one. So if your unknown was 1-butanol, you would draw the structure for 1-butanol going to 1-bromobutane. Procedure, third person passive voice. You should all be familiar with this by now. Don't forget that you do need to show units, and especially, some people are still forgetting, you need to include moles or millimoles for all of your reactants and catalysts, but not for solvents. So water was a solvent in this reaction, you would simply give volume. On the other hand, the sulfuric acid is a catalyst. You would need to give the concentration. Since it is a solution, you would need to state that it was concentrated or 18 molar and also report the moles. Of course, you always report yield and percent yield, and if you measure it, you would report melting point or boiling point. In this case, you should have a boiling point, and you will, in parentheses immediately after that, simply put literature and then give the literature boiling point that you're comparing it to. And always report spectral data at the end of the procedure. And you've seen this before as well. For IR, we identify the medium on which we obtained it, typically as salt plates of sodium chloride, the units, and then the frequencies of the various peaks. If it is a single peak, you give a single frequency regardless of how broad it is. If there are multiple peaks of the same type, you would give a range. For NMR, it is similar. The medium is a solvent, deuterated chloroform, so CdCl3. The units is part per million, and since we're not obtaining an actual frequency, we're using a proxy, we designate that. We're measuring chemical shift, and the symbol for that is the Greek symbol delta. So you could use a lowercase d and use a symbol font. But after that, we give the chemical shift, so 3.7. We give the splitting, a sextet, and then the integration, 1 hydrogen. And we do that for each peak. So semicolon, and then the next peak was at 1.7 ppm. It was a quartet, and integration was 2 hydrogens. And you can use the abbreviations SDTQM for singlet, doublet, triplet, quartet, and multiplet. But anything greater than a quartet, we spell it out. Obviously, for sextet, you can't use an S since it's already taken. But we spell those out. Calculations, limiting reactant, theoretical yield, percent yield. Should be fairly straightforward. Discussion. We'll start with the NMR, but all spectral data need to be presented in tables. This goes for both the NMR and the IR. For NMR, you have 5 columns. First one should be chemical shift. Second one is the type of hydrogen associated with that chemical shift, and in this case it will either be alkyl or alkylbromide, since those are the only types of hydrogens we're dealing with in this experiment. Splitting, again, triplet, sextet, doublet, quartet, etc. Integration, and these should be whole numbers. We can't have partial integrals, so this is the whole number integration of hydrogens, not the integral value that's given in red at the bottom of the spectrum. And then an assignment. So we are labeling which hydrogen is associated with each peak. And of course, for that to make any sense, you do have to have a structure. with the labeled hydrogens. So put that next to your table. And then, of course, any discussion you give should always be able to stand independently of the table, meaning if I delete your table, I should still be able to understand your discussion. So tell me what is there, then interpret it, and then draw your conclusion. Example is given here. There is a peak at 3.7 ppm. That peak is a sextet and integrates to one hydrogen. So even without seeing a spectrum or your table, I know at least part of your spectrum now, that you have a sextet at 3.7 ppm with an integration of 1. Then tell me what that means. 3.7 ppm is in the alkylbromide region, indicating this peak is the CH attached to the bromine. The splitting of a sextet means there are 5 neighboring hydrogens. That would suggest a methylene, or CH2, and a methyl, CH3 groups bonded to it. And then the conclusion, this peak corresponds to hydrogen B. And do that for each row. So going back a couple of slides here, so if we were doing the peak at 1.7, again you would state there's a peak at 1.7, splitting is a quartet, integration to 2 hydrogens. This is in the alkyl region. The quartet splitting indicates there are 3 neighboring hydrogens, and if you'll remember from our previous analysis, that 3 neighbors came from a methine, a CH, and a CH2, and again this would correlate with hydrogen C. So you're doing this for each row, should have a short paragraph just like that. Infrared should also be presented in a table. We've got an example here. Again, we have a range in this first row because we are typically going to be dealing with multiple peaks when we're looking at sp3 hybridized CH. The second row we have a single frequency given because it is a single peak. Okay, do the same, you will have 3 columns, wave number, characteristics, whether it's sharp, medium, strong, whatever, and then bond type, sp2CH, sp3CH, OH, whatever. When you are interpreting it, when you're doing your discussion, again, the discussion should be able to stand independently of the table, so describe what is there. Or there are medium sharp absorptions at 2900, 2970. Since there are multiple peaks, we give a range, and these are characteristic of sp3CH. This is probably all you will see in your spectrum, at least above the fingerprint region, above 1600 wave numbers. Remember, for IR, what is there is important, but so are peaks that are absent, in particular relevant peaks. Remember, your starting material was an alcohol, and so it's important to look to see if you have a peak for the alcohol, and if not, you should state so in your discussion. You would note that there is no peak in the 3300 to 3600 region, indicating an absence of an alcohol, because this does tell you that you do have an alkyl halide, not your starting material back. In fact, you could also mention the fact that there is no peaks for carbon-carbon double bond or for sp2CH. After all, one of the possible courses of this reaction would be an elimination. You're adding an alcohol and an acid. You've done this before, and you got an elimination forming a cyclohexene, and the absence of those peaks indicates that you did not get an elimination either. And that would be strong evidence then that you do have your alkyl halide. GC, this is not spectral data, but still presented in a table. In that table, you will list all of the standards and their retention times, and then you will have a final row which will list your unknown and the retention time for that as well. And then again, discuss it, state what is there. The chromatogram of the unknown shows a single peak with a retention time at 2.589 minutes. Then tell us what it means. That retention time is the same as that of 2-bromopentane. Again, give that retention time as well. Anytime you compare two values, always give the numbers so your reader can determine whether or not they agree that the numbers are close or that the numbers are the same. In this case, I state they're the same, and really, for all practical purposes, 2.859 minutes is the same retention time as 2.861. And then draw the conclusion. This indicates the unknown was 2-bromopentane. Boiling point and density, same thing. Present them in a table. Again, you will have the boiling points and densities of all of the standards, all of the alkyl halides that are possible. And then also you'll have one row listing your alkyl halide. And again, draw the conclusion, compare the numbers, state the boiling point that you observed, and then compare that to the boiling point of one of the standards, and report whether or not they're close or possibly the same boiling point, and then draw the conclusion as to which alkyl halide you have. And again, each section you should draw the conclusion that is appropriate for that data. So while the GC may say you have 2-bromopentane, if the boiling point says that you have 1-bromobutane, you would state that. And any discrepancies between the data you would resolve at the summary or the conclusion paragraph. In this you would summarize the data. You don't need to do a reanalysis, simply state the NMR indicates the product is 2-bromopentane, the IR indicates it is an alkyl halide and not starting alcohol or an elimination product, and likewise indicate what the GC and the boiling point or density tell you, and if any of the data are at odds, you would reconcile them, determine which unknown you believe you have, and brief statement as to why you trust certain pieces of data over the others. This report will be graded out of 200 points, so you do want to put your best effort into this one.